Progressive Domain Adaptation for Thermal Infrared Object Tracking. Thermal infrared, TIR, object tracking has gained significant attention in recent years due to its applications in nighttime autonomous driving, video surveillance, and missile tracking. However, TIR tracking is more challenging than RGB tracking due to the low resolution, lack of rich texture details, and low signal-to-noise ratio of TIR images. Existing TIR tracking methods mainly focus on extracting discriminative features of TIR targets, but they suffer from a significant drop-off in performance when trained on RGB datasets due to the domain shift issue. To address this challenge, a progressive domain adaptation framework for TIR tracking, called PDAT, is proposed. PDAT makes full use of large-scale labeled RGB datasets to learn tracking universal priors and transfers them to TIR tracking using unlabeled TIR data. The framework consists of three main parts: Segment Anything Model, SAM-based data preprocessing, adversarial-based global domain adaptation, AGDA, and clustering-based subdomain adaptation, CSDA. The AGDA module uses an adversarial learning approach to roughly narrow the feature distribution of the overall TIR and RGB domains. However, simply aligning the global domain feature distribution is not sufficient for tracking tasks that require fine-grained features. Therefore, the CSDA module is proposed to align features in the subdomain with similar categories for getting more fine-grained feature transfer. The proposed global domain adaptation and subdomain adaptation modules progressively align the feature distributions of the TIR and RGB domains in a progressive training manner. Figure 1 shows that the proposed method can effectively align the feature distribution of the RGB and TIR datasets to achieve fine-grained feature transfer. The PDAT framework is evaluated on 5 TIR tracking benchmarks, including LSO-TB-TIR 100, LSO-TB-TIR 120, PTB-TIR, VTUAV, and VOT-TIR 2017, and demonstrates favorable performance. The main contributions of this work include proposing a progressive domain adaptation framework for TIR tracking, proposing an adversarial-based global domain adaptation and a clustering-based subdomain adaptation module, collecting a large-scale unlabeled TIR dataset, and generating a pseudo-label training set through the SAM model. The proposed framework can be categorized as a fine-tuning-based deep TIR tracker, which first trains a deep network on RGB datasets and then fine-tunes on a small-scale TIR dataset to adapt the feature to the TIR tracking. The PDAT framework outperforms existing TIR tracking methods, including pre-trained, training from scratch, and fine-tuning-based deep TIR trackers. The paper discusses the challenge of thermal infrared, TIR, object tracking due to the lack of large-scale labeled TIR datasets. To address this issue, a domain adaptation framework is proposed to transfer knowledge from large-scale RGB datasets to TIR tracking. This framework consists of 3 core components: Segment Anything Model-based data preprocessing, adversarial-based global domain adaptation, and clustering-based subdomain adaptation. The Segment Anything model is used to generate pseudo-label pairs from the collected TIR dataset, which contains 2,549 image sequences and over 1.48 million frames. This pre-processing step significantly reduces the time required for training and enhances the tracking speed. Adversarial-based global domain adaptation is employed to learn domain-invariant features that are not sensitive to image styles. A transformer-based style discriminator is designed to capture global dependencies within an image and differentiate stylistic attributes between the source and target domains. The feature extractor is trained with a least square loss function, aiming to generate features similar to the source domain and fool the discriminator. Clustering-based subdomain adaptation is proposed to achieve fine-grained feature alignment. This involves dividing the data into multiple similar subcategories and performing domain alignment on these subcategories. An online clustering approach is used to obtain pseudo-class labels for subdomain adaptation, and a simple voting selection mechanism is designed to choose the most suitable clustering results. The proposed method aims to effectively transfer the tracking prior learned in RGB images to TIR tracking, addressing the domain shift problem caused by different imaging principles. By leveraging large-scale RGB datasets and adapting to TIR tracking, this framework can potentially improve the performance of TIR trackers. The proposed method, PDAT, is a domain adaptation framework for thermal infrared (TIR) tracking, which aims to transfer knowledge learned from RGB datasets to TIR tracking. The framework consists of global domain adaptation and subdomain adaptation modules. The global domain adaptation module aligns the source and target domains using a domain adversarial loss, while the subdomain adaptation module fine-tunes the alignment using a clustering-based label selection mechanism. The proposed method is evaluated on 4 widely used TIR tracking datasets, including LSOTB-TIR100, LSOTB-TIR120, PTB-TIR, and VOT-TIR2017. The results show that PDAT outperforms state-of-the-art trackers, achieving the best success rate and precision on LSOTB-TIR100. Compared to the baseline tracker Siam-CAR, PDAT achieves an absolute gain of over 6% and 5% in precision and success rate, respectively. The subdomain adaptation module is formulated as a minimization problem, where the objective is to align the subdomains of the source and target domains. The module uses a clustering-based label selection mechanism, which selects the most informative samples for adaptation. The weights of the samples are calculated using the LMMD method, which takes into account the category weights and kernel functions. The training strategy involves a progressive training approach, where the global domain adaptation module is first trained, followed by the subdomain adaptation module. The entire framework is optimized using a composite loss function, which combines the global domain adversarial loss, subdomain alignment loss, and tracking loss. The results on LSOTB-TIR100 show that PDAT achieves the best success rate in precision, outperforming state-of-the-art trackers. The results on other datasets also demonstrate the effectiveness of the proposed method. The ablation study shows that the subdomain adaptation module is essential for improving the tracking performance. Overall, the proposed method provides a novel approach for TIR tracking, which can effectively transfer knowledge learned from RGB datasets to TIR tracking. The proposed method, PDAT, demonstrates significant improvements in tracking performance across various datasets, including LSOTB-TIR100, LSOTB-TIR120, PTB-TIR, VOT-TIR2017, and VTUA versus it outperforms state-of-the-art trackers in terms of normalized precision, success rate, and other metrics. The authors attribute this success to their domain adaptation method, which effectively transfers fine-grained features from the source domain to the target domain. The qualitative comparison between PDAT and several state-of-the-art trackers on the similar distractor and background clutter challenges of LSOTB-TIR100 is presented in Figure 4. This figure shows that PDAT achieves more precise tracking results compared to the baseline and other state-of-the-art trackers, especially when there are many similar distractors and background clutters. Figure 5 compares the confidence maps generated by PDAT and the baseline Siam-CAR on several challenging sequences of LSOTB-TIR120. It can be observed that PDAT significantly reduces interference from the background clutter and similar distractor, demonstrating the effectiveness of the proposed domain adaptation method in achieving fine-grained features transfer. The authors also conduct an ablation study to demonstrate the effectiveness of each component of the proposed method. The results are shown in Table V, which indicates that the Global Domain Adaptation Module, AGDA, and Subdomain Adaptation Module, CSDA, are effective in improving tracking performance. Overall, the proposed PDAT method shows superior performance in various tracking benchmarks and demonstrates good domain transfer capability and robustness for different scenarios. This research paper proposes an unsupervised dual-level domain adaptation framework for thermal infrared (TIR) target tracking. The framework aligns RGB and TIR domains on both feature and semantic levels, reducing misaligned samples and improving tracking performance. A partial domain adaptation network is designed to solve the negative transfer problem, using sample-level feature reweighting and channel-level feature selection to enhance similar samples and filter unshared features. The authors conduct an ablation study on the label selection mechanism in the clustering-based subdomain adaptation, demonstrating that more accurate class labels can enhance subdomain alignment. They also compared 3 pre-processing methods, showing that the SAMBASED method achieves the best performance on 2 benchmarks. The paper presents a comprehensive comparison of the proposed method with state-of-the-art trackers on the TIR 2017 dataset, demonstrating the effectiveness of the proposed framework. The authors also provide an analysis of the network architecture, showing that the progressive domain adaptation can obtain better feature alignment and transfer effect. Furthermore, the paper highlights the importance of self-supervised selection of similar samples and features for domain alignment in tracking tasks where both source and target domains do not have class labels. The authors construct the largest scale unlabeled TIR dataset to date, which is useful for unsupervised and self-supervised TIR tracking. The paper concludes by discussing the significance of the proposed framework, which aligns RGB and TIR domains on both feature and semantic levels, and solves the negative transfer problem using a partial domain adaptation network. The authors demonstrate the effectiveness of the proposed method through comprehensive experiments and analysis. Recent advancements in object tracking have led to the development of various algorithms and benchmarks. The high-performance long-term tracking with meta-updater approach, 34, utilizes a meta-updater to adapt to changing object appearances. In contrast, the infrared object tracking algorithm with temporal features fusion Siamese network, 35, leverages temporal features to improve tracking performance in infrared images. The transformer tracking with cyclic shifting window attention, 36, and mixformer end-to-end tracking with iterative mixed attention, 37, methods employ attention mechanisms to selectively focus on relevant features. The Know Your Surroundings, exploiting scene information for object tracking, 38, and learning discriminative model prediction for tracking, 39, approaches exploit scene information to improve tracking performance. Several benchmarks have been proposed to evaluate object tracking algorithms, including the large-scale high-diversity thermal infrared object tracking benchmark, LSOTBTIR, 41, and the thermal infrared pedestrian tracking benchmark, PTBTIR, 42. The visual object tracking VOT 2017 challenge results, 43, and the visible thermal UAV tracking benchmark, 44, provide additional evaluation frameworks. To provide insights into the decision-making process of deep networks, the GRAD-CAM visual explanations from deep networks via gradient-based localization, 45, method has been proposed. This approach uses gradient-based localization to highlight important regions in the input image. The Deep Subdomain Adaptation Network for Image Classification, 40, method has been proposed to address the issue of domain shift in image classification. This approach adapts the model to the target domain by learning a subdomain invariant representation. These approaches and benchmarks have contributed to the advancement of object tracking research, providing insights into the development of robust and efficient tracking algorithms.